So I'm going to speak about the non-Lefschetz locus for lines and for conics, and my work is mainly inspired by the paper of Boy, Migliore, Mirarok, and Nagel about the non-Lefschetz locus. So the setting that I'm working, we have algebraically closed field K of characteristic 0, and R for me is the polynomial ring in n variables that I consider as a graded ring, and A is an Artinian graded algebra. I will denote by HT the Hilbert function on of A, so HT or HTA, depends if I need to specify what I'm talking about. And this is the dimension of the great piece, of homogeneous piece of T of A. So this is the setting I'm working. We already saw that, like, we say that A has the weak Lefschetz property if exists an element, a linear element, such that the multiplication map from degree A, degree T plus 1, is as maximum rank for each I. And the thing that we're going to study are the elements that actually don't have this property. So we know that, like, an element that have this property, L, is called a Lefschetz element. And the set of the Lefschetz element is like a Zariski open set in the linear forms. So we'll, Boy, Migliore, Mirarok, and Nagel study the non-Lefschetz locus that is defined as the set as the L such that is none. And the study is give to the non-Lefschetz locus a subscheme structure as a subscheme of Pn-1 dual. So the idea behind my talk is actually extend this, but instead of just looking at degree 1. So here there is the multiplication between AT and AT plus 1. I want actually to consider like multiplication of degree 2. So, but not just like L square, but even for any other homogeneous polynomial of degree 2. So I want to define Lefschetz conics. So the first part of my talk will be define what is a non-Lefschetz locus for the conics. And so the first thing that I need to do is define a Lefschetz conics. So I take a homogeneous polynomial of degree 2, and I say that C is conic if the multiplication map times C from AT to AT plus 2 has maximum rank for each T. And in the same way, I want to define the non-Lefschetz locus of conics as the conics that do not have this property. So the first thing that I need to do is actually define, so I'm as a set, I will call CA the set of conics non-Lefschetz. So I can see these as oh, yes, sorry, because this part is in n variables, and after I will just actually work in 3 variables, so that's why the reason I'm sorry, you're right. And I actually use, my main work is just in 3 variables, that's why I call it conics, but here it should be something else, you're right, I'm sorry. So, yep, whatever. So, okay, the first thing that I want to do is actually like give a scheme structure to this, because here I can definitely see this as a subset on P n, where n here is n plus 1 minus 1. But to study this, I want to give a scheme structure, and the idea will follow what is done in the paper of non-Lefschetz locus in the case of lines. The same thing I will do for this case. I'm working with a homogeneous polynomial of degree 2. So let's start. So this one is that you can see this as the union, where C is of degree 2, and the multiplication between AT and AT plus 2 as not maximum rank. So, sorry. So I can actually see, like I just check the degree T, and I check where fail to be maximum rank in degree T, and the non-Lefschetz locus for, in this case, is the union of all of this. So let's first define a scheme structure on this one. Clearly, we can have a map between R2 and AT plus 2 that takes my polynomial of degree 2 into a matrix that is choose a base for this and this. This one is represented by a matrix that is HT plus 2 times HT. And C is fail to have maximum rank in degree T only when this metric here does not have maximum rank. So is less than max HT. So this matrix, it depends by the coefficient of T. Therefore, the idea is actually, let's introduce S as K A1 AN, the coordinate ring for N. And we think about this as the coefficients of my polynomial of degree 2. So square x1, x2. So the multiplication map by C, multiplied by C, give me a multiplication between S tensor A that in each degree. So if I just go to look in degree T, this one is represented by a matrix that I call BT. And this matrix is a matrix that is age T plus 2 times age. And the entries of this matrix are linear form in the dual variables. So each entry is a dual form, is a linear form in these variables. And therefore, we can define this as the subscheme of Pn defined by the maximum minus of this matrix. So ICAT is minus of BT. And in the same way, I can define the non-Lefschetz locus in general as the subscheme defined by the intersection on all of all the ideas. So okay, some things that we need to recall is, since we define CA in degree T as a subscheme associated to a ideal of maximum minors, we have expected codimension. So the expected codimension is given by age T plus 2 minus h t plus 1. And moreover, in the case when the expected codimension is achieved, we also know that the expected degree is achieved. That is given by h t plus, assuming h t plus 2 bigger or equal to h t. But this gives us the expected codimension and the expected degree only for the conics that fail in, the homogeneous polynomial degree 2 that fail between degree t and degree t plus 2. And we actually want to study, in general, the ones that doesn't have this property for they exist at t such that they don't have this property. So the first thing that we want to ask is it a case where actually I can just look at one specific of these ideas instead of actually taking the union? So we want to recall that, like when we consider the non-Lefschetz locus from lines, we have that position from we have the if A is an Artinian doublet algebra, then it's enough checking the middle degree. So the ideal that define the non-Lefschetz locus, yes, sorry. The ideal that define the non-Lefschetz locus of so-called degree E is exactly the one in the middle. So and I will say that in this case, the non-Lefschetz locus is constant just in one degree, in the sense that we have an inclusion of ideals. And we want to check if something similar happened also for the case of degree 2. So, yes? Yeah, minimum. Yeah, sorry. The rank needs to be, it is not maximum, so it would be smaller than the least of the 2. Okay, so we want to try to prove something similar also in the case of polynomial degree 2. And so the first thing that we have is, so let's assume that A is an Artinian algebra. For now, I don't assume that this is Gaussian, but I'm assuming that HT is less or equal than H t plus 2, that is less or equal than H t plus 4. And that I don't have Socle in degree t and in degree t plus 1. So I want to have not Socle in this 2 degree, and I want to have like the Hilbert function t smaller than the t plus 2, smaller than t plus 4. In this case, I can actually prove that they have a containment, like even in the idea, so even as a scheme. So I will have that then. It's true. Is actually containment in. Therefore, if you are looking at the case of the Gaussian algebra, and I also assume to have in the weak Lefschetz property. In this case, I can actually conclude then The middle is actually the only thing that I need to check. So E minus 1, actually minus 1. So if I have a Gaussian algebra with the weak-Lefschetz property, then it's enough actually to check the middle degree. I need weak-Lefschetz property because first it will imply the function to be unimodal, and therefore I can actually just check the middle two using that one. But to make actually a connection between those, I actually need the weak-Lefschetz property in this case. Okay, so this is like the general definition, and from now on, I will just work in the case of three variables. So here R is just k, x1, x2, and x3. So things that we know in this case is first, and we are also looking at complete intersections. So A is R of 3 is an Artinian complete intersection. Then in this context, things that we know is theorem from Arima migliore Notre. Sorry. We know that like all of these complete intersections that are Artinian in three variables have the weak-Lefschetz property. Moreover, from Boy migliore Miroroi and Nagel, we know that for a general complete intersection, the non-Lefschetz locus for the lines have the expected codimension. Okay, so the main goal is actually generalize this last result and check that for a complete intersection in three variables, also looking at conics, we have that the expected codimension is achieved. To do so, I first actually need to take a step back and generalize the setting that I'm working on and talking about jumping conics and jumping lines. So the idea is we want actually to describe in some way the elements that are in the non-Lefschetz locus for line and for conics for a complete intersection. And actually we can generalize this instead of looking just at complete intersections. Florence, Failla, and Peterson actually start to look at all the finite length models that arise as a cokern of this map, a map like this. So 2 minus A. So we want to look at all possible models of this type that are cokern of a map like this, and with the hypothesis that this M needs to have finite. So clearly, when n is 1 and these are at 0, you are exactly in the case of the complete intersection, because in this case the map is just a multiplication for f1 and f3. And moreover, in these settings, if we call E the cocard, since M has finite length and we are in 3 variables, the Buchmann-Riemann complex is exact. And so we can actually see that if E is the specification of this is a rank 2 vector bundle over P2, and we have that for each T, is equal to MT. So the first cohomology module of E shifted by T is exactly the homogeneous part of degree T of M. Therefore, if I take the graded cohomology model that is defined in general as this, is the model that I start with. So using this idea, theorem from Failla, Florence, and Peterson, prove that this model here has always the weak-Lefschetz property. So to prove that this model has the weak-Lefschetz property, they actually checked how a generalized split on E, and use this to prove that that generalized is a weak-Lefschetz element. And so the natural question is this like also a necessary condition? So are exactly these lines the ones that are in the non-Lefschetz locus? So we have that the answer. So first, let's recall what is a splitting line, a jumping line is any line such that no. And we know, and this is theorem, we know how a generalized splits on a rank 2 vector bundle using Grauter-Mulich theorem, and for the unstable ones, using the work of Failla, Florence, and Peterson. So here, if E is a normalized rank 2 vector bundle over P2, we have that in the case, so first, if E is semi-stable, then NL is a general line. E splits over L as follows. So the splitting type will be 0, 0, or the splitting type will be 0, -1, depending if the Forster class is 0 or if the Forster class is -1. And this is like Grauter-Mulich theorem for the semi-stable ones. Failla, Florence, and Peterson actually extend this to the case unstable. And we have that in this case, this depends. So the splitting type will be K minus K from C1, 0, and is minus K minus 1 K from C1 minus 1, where K is the instability index. So in the case where C1 is 0, we have that is strictly bigger than 0. In the other case, is bigger or equal than 0. Because the stability is the list such that H0 of shift of Manu K is non-zero. So after that is always 0. Okay, so now we have this, and we can actually check if the the condition of splitting like a general line is also necessary for have the weak Lefschetz property. And we have theorem. So the non-Lefschetz locus of M, the non-Lefschetz is exactly the set. And this also gives us a way to check if the codimension in general is achieved or not. And so we have that if M is as I defined above, and so 1 with and E is general, then we have that the expected codimension is achieved in particular. So the codimension E will be 1 in the case E unstable, or in the case that see 1 is given, and is actually 2 in the case when is stable with the fourth shell class odd. So for the lines, we have exactly the same thing. Like the non-Lefschetz locus of line is exactly the set where of the splitting line. And so from here we're talking about line, we are going back to think about conics, and we can ask if this is true also for conics, especially for a smooth conic that we know how a general smooth conic splits. So to do that, so Halvitter actually give us as a smooth conic split on a rank 2 vector bundle over P2. And so we have that theorem. If C is smooth conic, and E is a rank 2 vector bundle normalized, then this splits like the splitting type is 0, 0 in the case where the fourth shell class is 0, and the splitting type is -1, -1 when the fourth shell class is -1. So we want to check if this is also like the same thing for of the non-Lefschetz locus of conics. So if every conic in the non-Lefschetz locus is a conic that's split in this way. And unfortunately, the answer in this case is not positive. The non-Lefschetz locus is contained in the set of the jumping conics, but is not like necessarily the same thing. So a jumping conic is everything that doesn't split like this. And another theorem of Halvitter says that like the set of the jumping conics that it calls J2 it gives us a scheme structure that is like compatible to the one that we saw before, but like is a hypersurface in P6. It also tells us which one is the degree of this hypersurface, and so it also defines what are the jumping conics in the case where the conics is not smooth. I will not do this now, but like in the case where C is not smooth, the jumping could that are not smooth are in the closure of this. So, but like the important thing is in actually doing this proof as a corollary of this proof. Sorry? Yes, P5, yes. 6 variables, yes, sorry. As a corollary, sorry, I'm not sure how to spell corollary. We have that in the case that E is semi-stable, for C1, I assume normalized. If the Forcer class is -1, then the non-Lefschetz locus of conics and the jumping conics are the same thing. And in particular, we have that is a hypersurface E in P5. But this is not true when E always is semi-stable. In fact, let's C be a smooth conic. Then C is in the non-Lefschetz locus of conics if and only if the splitting type, in this case is 0, so minus A plus A, but with A bigger or equal than 2. So is a jumping conic when A is bigger or equal than 1, but to be in the non-Lefschetz locus, I need to be bigger or equal than 2. We can also extend, just to hold this definition to the case unstable, but position. Sorry? Sorry. Yeah, unfortunately, my L and my C are very similar. I need to be careful on that. Okay, so we can also extend this idea for the unstable, but in the unstable case, everything works nicely. So for the unstable, we have that C smooth. Then for C smooth, we have that C is in here if and only if C is conic. And also, we have that in general, this one is so the only case that we should care about is the case where E is semi-stable with the Forcer class even. And here, so we know that like in this case, the non-Lefschetz locus is contained in hypersurface, that is the one of the jumping conics, but it's not all the hypersurface. And we can actually compute which one is the expected codimension. For M, where M as above is 3 if E is stable. So here we are always Forcer class of is semi-stable, and it's 2 if E is semi-stable. Okay, so now that like the main question will be, is it true that this expected codimension is achieved in the case where E is general? And we can give a positive answer in the case of the complete intersections. For with assumption of generality. So theorem. Let's now return to the complete intersection of I3. So if you're looking at a complete intersection in 3 variables, in this case, so using what we know from before, we have that the expected codimension of CA, I mean, is 1 in the case where, so here E is the Sokal degree, that is D1 plus D2 plus D3 minus 3. So is 1 every time that if E is even, or if D3 is strictly bigger than D1 plus D2. This corresponds to the case where the vector bundle has a Forcer class odd, or the case where the vector bundle is unstable. And in this case, we know that it's hypersurface surface. We don't need any other hypothesis. So actually, this one is the codimension. Is true if D3 is equal to D1 plus D2. And so this corresponds to the case where it's semi-stable but not stable. And it's 3 if D3 is strictly less or equal than D1 plus D2 minus 2, and the Sokal degree is odd. So theorem, if A is general CI, then CA as expected. So in the case of the general complete intersection, we have that the expected codimension is achieved with the hypothesis of generality. If we don't have the hypothesis of generality, this is not true. In fact, the examples, this example that we can have is with the monomial complete intersections. And so let's, in the case, for example, if I take the monomial complete intersection, this one here, R, so A is x1, x2, x3 over x1 to the second, x2 to the third, x3 to the 5. This one, we are in the case where D3 is equal to D1 plus D2. So we will expect the codimension to be actually 2, but we can compute that this one is hypersurface. Actually, every time that we have a monomial complete intersection with D3 equal to this, we will always have codimension 1. In the case instead where is the case where we expect to have codimension 3, is actually we can have all the possibilities. So we can have example where the codimension is actually 3, 2, and 1. So for example, so examples. So now we are looking at the case where D3 is less or equal than D1 plus D2 minus 2. And here the expected codimension is 3. But we have some examples where, let's start by an example where actually, and I think is the only one, where actually the expected codimension is achieved, and is the one x1 square, x1, x2 to the third, and x3 to the third. this one actually the codimension of these three. But we have also examples where it's 2 and 1 is 1. So for example, for A, R over x1 to the 4, x2 to the 4, and x3 to the 6. Here, the codimension of CA is 1. So we have again a hypersurface. And last example is when A is, the degrees are 3, 4. In this case, actually, the codimension is true. Okay, so this is all. Thank you.